Today we're going to talk about my favorite data structure. It's a tree. So what's a tree? Tree is not a linear data structure. So before that moment, we worked with linear data structures, for example, like linked list. So in linked list, we have pointer to the next element, and pointer to the pref element, right? In tree, we have pointers to some children. In this example, we have binary tree. Binary tree means that every node have two pointers to two children. For example, something like this. So let's talk about concepts of binary tree. So every tree have trees in programming like working a little bit backwards. They grow down, not up, like real trees. So our most top element, it's a root of a tree, and this root have branches. So branches, like real tree, branches is like connections, not connections, but parts of the tree that lower than our root. So in this example, we can see that our left branch is everything on the left side, and right branch everything on the right side. Also in trees, we have such concept as a leaf. So leaf, like in a real tree, is an element that don't have children. So in this example, we can see that those elements don't have references to other elements, like don't have children, so those elements are leaves. And tree have a depth. So you can see that depth is like the height of the tree. So height of the tree calculates by the deepest element. And if we will create one more element here, height of our tree will be 4. But right now, who can tell me what's the height of this tree? 3, right. So it's a basics of binary trees. Let's talk about implementation. So I think you will like it, because let's do a revision. So we have an implementation of linked list. So we have class node, and we have, for example, int value, and we have pointer to the previous element, pointer to the next element, and like some methods to work with this node. What we need to change in this code, so this node became not a linked list node, but a tree node. something like this, but in binary tree, we have such concepts like left and right. So
Okay, so left and right.
Left next, right?
Left and right, and maybe we need to have a parent. Okay.
uh,
Or not.
okay, so what we need, yeah, like the basic, yeah,
Val.
well, like data or key, yeah. So our code of node is not changing. We're just changing the names of those pointers.
All right.
And you said that we need also previous element.
Well,
We can do this, but in this example, we have the tree that don't have where we have tree where every node don't have reference to the previous. Okay.
Is this node a root node?
What?
Is this root node in our example?
It's just a node. It can be like any node. So if we will draw this node, it will look like the linked list node, but we will have left and right, and left will point on another element, and right will point on the right element, and so on and so forth.
So the branches cannot point to the previous.
It can, but it will not in our example. We can add like another variable like prev, and prev will point to the previous, but
we don't need that.
in this example, we don't need this, but it's possible. Okay, so like in binary tree, we have only left and right two children. In other tree, we can have 4 children, like child 1, 2, 3, 4. For some, like in some cases, maybe we need this, but now we are looking on the binary tree. Is this clear? So I can show you this beautiful slide. Like in the linked list, we have class binary tree where we can store our root, because our root is our like entry point into the our tree. Because if we have root, we can have an access to any element using those references like in the linked list. Is this clear? Okay. So maybe someone have questions about that. Okay.
Well, I guess we'll see then.
Okay. Let's create some example.
I have a question about that. We need to announce it separately, like it should be our like separate node.
No, it's like the head in the linked list. It's just a part of the our data structure, but we have a reference to this element in our main class, main object. So. For example, we have such tree. In trees, we have such thing like traversal of tree, because in linear data structures, like linked list or an array, we don't need special techniques to traverse our data structure because it's linear. We just need to go from one element to another. But in tree, to traverse tree, we can have like many techniques. So let's talk about those techniques. As you can see on the slide, we have two main like categories of techniques: depth first and breadth first. So depth first, that it's a techniques that concentrates on the traversing to the deepest element, and like traverse this way. And breadth technique based, it's when we traverse our tree layer by layer. So let's talk about three techniques, like deep depth based techniques. So first one is in order traversal of binary tree. If we will create some form of pseudocode, it will look like we go left, then we print, then we go right. What does it mean? So we now in our root, we checking if we have if our root have a left element, we go in the left element. It's recursive operation, so the same operation. If this element have a left reference, we go there. Okay. If this element have left reference, we go there, but it's don't have left reference, so we print this element. Recursively, we now back in our previous element, we do our print. Next, we checking if this element have right reference, we go there. This element have, will someone help me? What will happen next?
Check if 3 has left.
Yeah. Is it?
Well, it doesn't.
Yeah,
left
yeah, it's right.
doesn't, yeah.
Listen, continue.
Okay, so if 3 has left, it doesn't have left, so
Yeah.
we go back to side.
No, left, don't have left. Then what we need to do? Yeah, okay, we print 3. Then what we do?
Check right.
Yeah, no. So we go back in previous, we go back. We done our, like this operation, checking right. So what we need to do next? Yes. What we will do next?
Right, left we print, so right.
What?
We print.
Left we print, so we need to do right, like 0.
Yeah,
First of all, we print.
yeah, so we checked left. What we need to do next? Print, yeah. So another 3. Then,
Check the right,
yeah, we have.
print,
No,
Left
action.
left, right. Not right, but like,
Yeah.
yes. No. Yeah, okay. I needed to hear this. Okay, what we do next?
We print.
Yeah,
Then we check right.
yeah.
Here we check everything. We don't have left. We print. And we don't have right.
Mm-hmm.
Right. So I guess we go back.
Yes.
And here we are done with the operation. So in
Yeah, so this is our traversal, in order traversal. You can ask me, why we need many types of traversal if we will have like the same numbers but in different порядок?
Yeah. Order.
Why? Because we can have different situations and different problems that we will try to solve with tree. And now we see our like explanational int tree that doesn't make any sense. It's just for you to understand the concept of trees. But for example, there one problem with tree, one problem that trees can solve. We can build an arithmetical tree. What is this? So arithmetical tree looks like this. Every element, if it's not a leaf, it's some arithmetical operation. For example, this operation equal, right? Not what is this? Multiplication. For example, I don't know. Thank you. And leaves are numbers. For example, 5. Let's add one more here. So it will be plus, it will be 3, 4, and it will be division. And here now, if we will do our in order traversal, we will have our arithmetical arithmetic. Yeah. So let's do in order traversal once more time. Who will help me?
I want to.
You?
Yeah.
Okay.
Okay. We are at the root. We go left.
Yeah.
After we go left again.
Yeah.
When we go left, we check left. We don't have anything,
Mhm.
so we do print. We put 5.
Yes.
After that, we go back and we check right. We print.
Mm-hmm.
First of all, we print and then we check right.
Mm-hmm.
At the right, we check if we have left. We
Mhm.
have left. So left is 3. We print 3. 3 doesn't have like left. Okay, we don't have left. We print it. It doesn't have right, so we go back and we print plus.
Mm-hmm.
We check right. We don't have anything at the right, so we go back to
Uh,
to minus and to.
Yeah. We
Yeah,
have a
we go back to
problem.
minus, we don't print it. And we go back to multiplication and we print it. But
Yeah. One moment.
Yes, we need to use a note for 3 plus.
Yeah. Yeah.
I guess so.
Example 2.
Yeah, we go to 2, we print 2, then we go to basically to the minus, we did everything at the minus, we go to multiplication
Yeah.
and we print it. Then we go back, we go to, I don't know how it's called, division.
Yeah.
We go to division, we check left. We check left, we have 4.
Yeah.
4 doesn't have left or right, so we print it. We go back to division, we print it, and then we check right. Right doesn't have left, so we print it, and it doesn't have right.
So
And so on.
now we have our arithmetical. Once more, arithmetical what? Expression. Yeah. So we can like show our arithmetical expression as a tree, and with help of in order traversal, we can solve this expression. And you can see that our expression is very simple, but imagine very huge tree with very maybe time expensive operations. It can help with optimization, and it's only one example of task that you can solve with trees. And I love trees for this reason, because sometimes you have task and you don't know how to solve it. And my favorite способ solve a problem, do it with help of trees, because trees are very flexible and customizable. So what I want to show and tell you that sometimes that those trees that we are learning now and those traversals that we are learning now, it's maybe you will never use tree with some indexes, but you totally will become a better programmer and engineer if you will understand the concept of tree, because it's very useful in your future career of programmers. So it's a little motivation. Here you can see the code of in-order traversal. It's very simple. It's so simple. I can't. Like it's we just do recursively. Like we check if our node exists, and then we just recursively call this method for the left reference. Then we print. Then we call it for the right reference, like in this pseudocode. Is it clear? Maybe someone have questions about what I just told. Okay. Okay. Pre-order traversal. So the same, like very same concept, but what we do here is we print, then go left, then go right. So for example, now we need to print left, right. So I don't know, Andrei, can you help me? Can you tell me what in what order we will print our elements with pre-order traversal if we have such pseudocode for this operation? Yeah. So what I need to print? We're starting from this element, right? So yes, so we print an element, then yes. Yeah, we're printing 1, then we go left, printing 3, then yes, yeah. We go right. Mm-hmm. Yeah. Then
now we need to go back to beginning and go to the right direction.
yeah, so great. And in right section, the same logic. Is this clear? Okay. Maybe someone have questions about this one. Like with this traversion, we can use this traversion to copy tree, because to build a tree, we need to start from the root and the whole, from the root, to its left child, to its left child. So this traversal we can use to copy the tree, because if our copy algorithm will work like we add root, then we add left. If it's don't have left, if it's have left, we add right. Then we will be able to copy the tree. And last but not the least, post-order traversal. I don't want to stop on this one too long, because it's the same. It's the same, but now we go left, then we go right, then we print. Like, is this clear? Okay, let's move on. Also, we have level order traversal. As you can see on this picture, we go like level by level. We print 5, 12, 13, 7, 14, 2, and so on. An algorithm of this method is a little bit, it's not little bit, but it's more complex, and I don't want to stop on this. If you want, you can check it by yourself, but the main principle of this algorithm is that we use a queue, and we add our element into the queue. And at the end, we will have a queue filled with our elements level by level. Okay. And one more very important topic is binary search tree. So in binary tree, we can have elements that are random. So we can have any elements in any position of the tree. In binary search tree, we have an example of sorted tree. So every root have elements on the left side that are less than a root, and every element on the right side from the root are bigger. It's pretty similar to the quicksort, maybe, because if we will look on the our root as a pivot, it looks a little bit familiar. Okay, so when we are building our binary tree, when we insert an element in binary search tree, we need to check our root first of all. So if we have an empty binary search tree and we want to add an element, for example 5, we will make 5 our root element, because we don't have any elements before in the binary search tree. Then we want to insert element 3. We check if 3 less than 5, it will become the left child. So we will create our node 3, and for the 5, we will set our reference left for 5, because 3 is less than 5. Then we want to add 6. No, we want to add 10. We add node 10, and we check. If 10 less than 5, we need to go in the left element, but 10 is greater than 5, so it became the right element, right child. Then, for example, we want to add 4. Okay, 4 is less than 5. But 5 already have a left child, so we go to the left child of 5. And now we do the same operation here. If 4 less than 3, 4 not 4 actually greater than 3. So if 4 greater than 3 and 3 don't have a right child, we create a reference, like right reference for 3, and now we have such data structure. Okay, Bogdan, if I want to add, for example, 8, what I need to do? Yeah, but what's the algorithm? Like, no, we start from the root element. Why 10? We are adding 8. We want to add 8 in our tree, binary search tree. So the 8 like have only one position where it can be in our sorted binary search tree. Maybe someone wants to help Bogdan. What we need to do? Yeah.
First of all, we check if we compare 8 and 5. 8 is greater than 5, so we go right. But we already have a right child, we have 10.
Yeah.
So now we compare 10 and 8, and 8 is less than 5, so we go left. And well, we don't have a left child, so we add 8 to the left of 10.
Right. So, for example, if we want to add 12, we check 12 bigger than 5, 12 bigger than 10, so 12 will be here. And now, if we want, why binary search trees are great is because they helps us to insert, delete, and find elements very quickly with big O log n. Because, for example, if we want, it's like binary search in an array. So if we want to find 8, what we need to do? We need to check if 8 bigger than our root, we go right. If 8 less than our like current element, we go right. If 8 less, we go left. If our current element equals our element that we were trying to find, like we found this, and we can like print some information about this. So we can find any element very quickly, and the search of element very similar to the insertion of the element. Yeah.
Yeah, I have a question. Like, am I right that if we do like the first, the first method of traversing the tree, then we'll have a sorted list? Like if we do like the first, like where we have left, print right.
Yeah.
Like we will have the sorted list.
Also, in order traversal, in binary search tree will give us an output with sorted elements. Yeah. And I wanted to like show you this with your assignment, but thank you, Igor. Like killjoy. Okay, so maybe someone have questions about binary search trees.
What if we add in some elements such as, for example, we have 12, we add 12?
If in our node we only have value and our node is completely similar to the node we're trying to add, we just not add anything. So in this example, if we want to add 10, we can see that we already have 10 and we just don't add anything. If in our node we will have another information except our key with which we store, then we can like decide for ourselves. For example, we can say that all equal elements go to the left side. In such case, all equal elements will be on the left side. It's like the basic rule that, for example, if our new element is less or equal to our current element, then it goes to the left. Or we can say that our element go to the right side. Like you decide for your needs. Or you can say that the same element is not, we are not saving it because we already have this.
So if it's just a simple integer, it's become a set person.
Yeah. Other questions? Okay. I think you will have questions while assignment. So, yeah. The good news, I don't know, Sergey, can I tell good news or you changed your mind about?
Keep it.
Okay. So. Okay.
There's no good news.
Yeah, but there are no bad news. It's good too, right? So what you need to do is to create binary search tree class and create node class. You need to create method insert for binary search tree. This method needs to like receive an integer and place it in right position in your tree. Then you need to declaratively assign like 10 or maybe more elements with your insert method. Then you need to implement in order, pre-order, and post-order tree is like hardest task from all of those because those methods very different from each other, right? And display results in console and draw your tree on a paper. So you will have a set like an array or just like a set of numbers. And you will build your tree inside your computer with your program. And also please draw your tree on a paper. And one optional assignment is to implement a method high. And method high needs to give you your high of your tree. So in this example, high of tree is like 2, right? Or 3. Who will tell me? 2, right. And if we will have such example, what high will be? And if we will have such example, yeah. So high, we can calculate high by the like deepest element in the tree. If you have any questions about this, you can ask me, Valia, or Sergey in any time. Don't wait until the end. If you like blocked, ask for help. So that's it. Thank you. Good luck. Thank you.